You think space should be full of stars, right? Because when you look up at the night sky on Earth, you see thousands of points of light, and you know that is only a tiny fraction of the universe. According to NASA's estimates, there are over 100 billion galaxies, and each galaxy contains hundreds of billions of stars, meaning that logically, if you leave Earth and look out into space, the sky should be glowing in every direction. However, when you look at images taken from the International Space Station, you see the exact opposite. The background behind the astronauts and the Earth is an absolute black. No stars, no light, nothing at all. This is where the real question arises. If stars are truly everywhere, why don't you see them? Let's take a specific example, a real moment, not theory or speculation, but one of the most famous images ever captured in space. On February 7, 1984, when Bruce McCandless II performed the first untethered spacewalk in history, he ventured away from the Space Shuttle Challenger while orbiting about 300 kilometers above the Earth. For the first time, a human was no longer attached to the ship by a safety line, but moved completely freely thanks to the MMU system, a small propulsion device mounted on his back that allowed him to float in the infinite void. If you look at the photo taken with a Hasselblad camera at that moment, you will see an almost unbelievable image. A tiny human floating above the giant blue planet, with nothing holding him back, nothing around him, just space. But there is one detail I want you to focus on, not the human, not the Earth, but the background. It is completely black, with no stars, no light, and no sign of the hundreds of billions of stars you know exist. This is not an isolated case. If you look back at photos from the Apollo program between 1969 and 1972, you see the same thing repeated, a pitch black, empty sky. Even when astronauts like Neil Armstrong stood on the surface of the moon and looked up, they reported that they did not see stars in bright light conditions. At this point, you have to stop and wonder, if both the camera and the human eye cannot see stars in the same circumstances, then the problem cannot simply lie with the equipment or the perspective, but must lie in something deeper, a more fundamental principle that we don't truly understand yet. To understand this seriously, we have to set aside intuition for a moment and look at how a camera actually works. A camera does not see the world the way you think. It doesn't know what is important or unimportant. It is simply a device that captures light, or more precisely, captures photons over a certain period of time that we call exposure. That duration can be very short, like 1/4000 of a second when you shoot in bright sunlight, or last several seconds when you shoot in the dark. This creates a very fundamental trade-off that you may have experienced with your phone. If you want to see very dim things, you have to let the camera look longer. But if it is something very bright in the frame, it will quickly become overexposed and lose all detail. Now, bring that simple logic into space, where things become much more extreme than on Earth. At Earth's orbit, the light from the sun has an intensity of about 1,361 watts per square meter, a staggering number compared to any artificial light source you are familiar with. This means that everything directly illuminated by the sun, from the white spacesuit to the surface of the Earth below, becomes extremely bright. They are so bright that if you don't reduce the exposure time to a very low level, the image will be completely saturated. But in that same frame, you have stars, light sources at distances of light years, even thousands of light years. By the time their light reaches the camera, its intensity has decreased millions or even billions of times compared to the light reflected from an astronaut right in front of the lens. This is the core issue, because the camera has no way to process such a large range of light intensity in a single shot, what we call dynamic range in photography. Even though modern sensors can handle a fairly wide range, usually around 12 to 15 stops, equivalent to a difference ratio of about 1/4000 to 1/3000. That figure is still too small compared to the reality of space, where the difference between an object directly lit by the sun and the light from a distant star can exceed millions of times. This means the camera is forced to choose, not by the photographer's will, but by its own physical limits. If you choose an exposure to preserve detail in bright objects like the astronaut, the Earth, or the spacecraft hull, you must use an extremely fast shutter speed. In that tiny fraction of time, the number of photons coming from the stars is too few to create a signal strong enough on the sensor. They are completely drowned in electronic noise and never recorded. This is why the sky in those photos looks completely black. Not because nothing is there, but because the signal is too weak relative to the device's detection threshold. If you try to do the opposite, increase the exposure time, keeping the shutter open longer to collect more photons from the stars, then everything closer will immediately become too bright. The pixels on the sensor saturate, all detail is lost, and the entire image will be blown out white, containing no useful information. You might think, why not take two photos, one for the bright object and one for the stars, and stitch them together? In fact, that is exactly how astronomers work, but that doesn't reflect what a camera records in a single actual moment, especially in space missions where the main goal is to record people and equipment in bright light conditions. If you look at photos of the starry sky taken from Earth, you will realize that they are usually taken with long exposure time, sometimes up to tens of seconds or even minutes, in a completely dark environment where there are no competing bright light sources. That is a condition you simply do not have while floating in space near Earth under direct sunlight. This brings us to a very important point I want you to understand. The camera does not ignore the stars. It does not hide them. It simply does not receive enough signal to record them under those specific conditions. This is not a subjective choice, but an inevitable consequence of physics, a limit that any light-capturing system must face. When you start to look at the problem this way, you see that the absence of stars in photos is not suspicious. It is actually evidence that everything is working exactly according to what the laws of physics predict. Once you understand how the camera works, you begin to realize that this is not a random phenomenon occurring in a few individual photos. It appears consistently in every space mission we have ever conducted. From the first photos of the Apollo program between 1969 and 1972 to modern images and videos live streamed from the International Space Station, I want you to really stop and think about that. If there were a mistake, if there were a staging, if there were something wrong, it couldn't be repeated perfectly over decades, across thousands of different devices, through hundreds of different astronauts, and in countless different conditions. Interestingly, you don't just see this in still photos, but also in real-time live streams, where there is no chance to edit or stage, where you can see the Earth rotating slowly below, see the astronauts moving, see the sunlight reflecting off the spacecraft surface, yet the background sky always remains an absolute black, unchanging, unwavering, without any sign of the stars you expect to appear if your intuition were correct. NASA has recorded millions of such frames over more than 2 decades of continuous ISS operation, using various types of cameras, from specialized film cameras to modern digital cameras with CMOS sensors of increasingly high dynamic range, sometimes up to 14-15 stops. You might think that with better technology, we would start to see stars appear in these conditions, but that's not the case. The limit does not lie in the camera not being good enough. It lies in the massive difference in light intensity between objects in the same frame. This remains unchanged regardless of how much you upgrade the equipment, as long as you are still shooting in direct sunlight. If you watch live streams from the ISS during the daytime, you will notice very clearly that the sky behind the Earth is always pitch black, even though you know thousands of stars are right there behind that background. This isn't because the camera forgot to record them, but because their signal is too weak compared to the bright light from the Earth and the spacecraft. More importantly, this phenomenon does not depend on a specific type of camera or a specific configuration. It happens with every optical system, from the Apollo-era Hasselblad cameras to the modern digital cameras mounted on the ISS, and even the commercial cameras you can buy on the market. If you take them out into space and shoot in the same conditions, you will get the same results. This is a sign that we are not facing a technical error, but a fundamental principle, a law that every light capture system must obey. In science, when a phenomenon is repeated consistently over time, devices, and people, we no longer consider it a coincidence. We consider it evidence, an indicator that there is a deeper law operating behind it. This is when you need to change the way you ask your question. The original question, why don't we see stars in a photo, is not enough. The correct question should be why. In all conditions with bright light, do we not see stars? When you ask the question this way, you begin to realize that the problem does not lie with each individual photo, but with how light interacts with our observation system. This also explains why even astronauts, when looking with the naked eye in bright light conditions, reported that they did not see stars. The human eye, like the camera, faces the same limits regarding dynamic range and light adaptation. When you combine all these things, you start to see a clearer picture. Your intuition about the universe, built from experiences on Earth, where the atmosphere scatters light and softens the contrast between light and dark, no longer applies in the vacuum of space. In space, light is not scattered. Shadows are truly absolute darkness, and the difference between light and dark becomes so extreme that our observation systems, whether cameras or the human eye, must choose one part of reality to display and ignore the rest. When you understand this, you will see that the repetition of this phenomenon over decades is not suspicious. On the contrary, it is the strongest sign that everything is working exactly as physics predicts, and that the error lies not in the photos, but in how we expect the world to look based on our initial intuition. The key point you need to understand now lies in an extremely basic physical law that has powerful explanatory force. Light intensity decreases according to the inverse square law of distance. This means that when the distance between you and the light source doubles, the amount of light you receive decreases to 1/4. When the distance increases tenfold, the light decreases to 1/100th. If you continue to expand this law to the scale of the universe, where distance is no longer measured in meters or kilometers, but in light years, that reduction becomes so massive, it almost exceeds your intuition. 1 light year is equivalent to about 9.446 trillion kilometers. And many stars you see in the night sky are actually located tens, hundreds, or even thousands of light years away from us. That means the light you receive from them has been diluted through an almost infinite space. This is why, although stars can be extremely bright at the source, by the time their light reaches you, it is only a very weak signal, a signal enough for you to see when the surroundings are completely dark, but absolutely not enough to compete with any strong light source nearby. To give you a clearer picture, take the example of Sirius, the brightest star in the night sky that you can see with the naked eye. It has an apparent magnitude of about 1.46, and although it is brighter than all other stars you see, its light is still millions of times weaker than daylight on Earth. Sunlight hitting the Earth's surface can reach about 100,000 lux on a sunny day, while the total light from the entire starry sky is usually only about 0.001 lux, or even lower, a difference of up to tens of millions of times. When you bring this into space, where there is no atmosphere to scatter light and soften the contrast between light and dark, that difference becomes even more harsh. Sunlight shines directly on astronauts, on spacecraft, and on the Earth's surface with maximum intensity, while the light from the stars remains at its feeble level. As a result, 2 completely different worlds of light exist in the same frame, one extremely bright and one extremely dim. Your observation system, whether the human eye or a camera, cannot process both simultaneously. It is forced to choose. When it chooses to display bright objects, everything weaker disappears from your perception, not because they don't exist, but because they are completely overwhelmed. You can think of this like standing under an extremely powerful stage light. You cannot see the small lamps in the distance, not because they are off, but because the light around you is too strong. In space, this effect occurs to a much more extreme degree because the difference is not several times or several dozen times, but millions of times. When you understand this, you begin to see that not seeing stars in photos or with the naked eye is not an anomaly. It is actually the only thing that can happen according to the laws of physics. This is the most important point I want you to grasp. The stars do not disappear. Their light does not cease to exist. But in bright light conditions, especially when the sun is shining directly, their signal becomes too small compared to the bright background, to the point that your observation system simply cannot record them. When you pair this with what we discussed about exposure and dynamic range, you will see that this entire phenomenon is not a mystery, but a completely consistent consequence of how light propagates in the universe and how observation systems interact with that light. If you think the problem lies only with the camera, then we haven't gone deep enough yet. Even if you discard the camera and use your own eyes, you will still encounter that exact same limit. This is when we need to talk about how the human eye actually works as an optical system. Essentially, your eye is also a light receiving device, a biological camera with components similar to a lens, aperture, and sensor. Interestingly, human eye has an excellent ability to adapt to light with a total dynamic range that can reach $6 under full adaptation conditions, meaning it can process a much larger light difference than a camera. However, the crucial thing you need to understand is that this capability does not happen simultaneously, but over time through the process of adaptation. This is precisely the point your intuition often overlooks. When you are in a very bright environment, such as standing on the surface of the moon under direct sunlight, your eye does not operate in dark sensitive mode, but in light sensitive mode. This means your pupils constrict, just like when you go out into harsh sunlight on Earth, to limit the amount of light entering the eye and protect the retina. This significantly reduces the ability to detect weak light sources. This is not a hypothesis, but something recorded during the Apollo missions from 1969 to 1972, when astronauts like Neil Armstrong and his crewmates reported that they could not see stars while standing on the lunar surface in bright light. This might sound strange if you hold on to your intuition from Earth, but when you understand how bright that environment truly is, it begins to make sense. The lunar surface reflects sunlight quite strongly, with an average albedo of about 0.12. When you combine that with the lack of an atmosphere to scatter light, you get a direct, sharp, and high contrast light environment, equivalent to a very harsh sunny day on Earth, and in some conditions, even more extreme. In that environment, your eye is forced to adapt to process the large amount of light from nearby objects. When it does so, it sacrifices the ability to see weaker signals, such as light from distant stars. You can imagine this like walking out of a dark room into daylight. You can hardly see any stars in the sky, even though they are still there, because your eyes are in bright light adaptation mode. To see stars, you need to be in the dark long enough, usually 20 to 30 minutes, for the rod cells in your retina to increase light sensitivity, a process physiologists call dark adaptation. This is exactly why you can see a star-filled sky at night on Earth, but not when standing in bright light. This is exactly what happens in space, where astronauts are almost always in bright light conditions when observing outside the ship, and therefore their eyes never reach a sensitive enough state to detect the weak light from stars. If you start comparing this to a camera, you will see a very clear similarity. Just as a camera must choose a specific exposure level, your eye must choose a specific adaptation state at a given time. In both cases, that choice is determined by around the environment, not by your will. When the environment is dominated by strong light from the sun, every observation system, whether electronic or biological, is pushed into the same limit where weaker signals are eliminated. This leads us to a very important conclusion. Not seeing stars in space is not due to a poor camera or human eyes not being good enough, but because both are working exactly the way they were designed to work. following the same physical laws of light and the same signal processing limits. When you look at the issue from this perspective, you begin to see that the camera and the human eye are not two different systems giving two different results, but are actually two expressions of the same fundamental principle, a principle that states that in a world where light can differ by millions of times, any observation system will be forced to ignore one part of reality to display the rest. This brings us to an even more critical factor you need to understand. The process of light adaptation in the human eye does not happen instantly, but takes time. Not just seconds, but tens of minutes. When you move from a bright environment to a dark one, your eyes must undergo a series of complex biological changes to increase sensitivity to low light. This process, which visual physiologists have studied thoroughly since the early 20th century and continues to be confirmed by modern research, shows that to reach maximum sensitivity in total darkness, the human eye needs about 20 to 30 minutes. During this time, the rod cells in the retina, responsible for vision in low light conditions, gradually recover and increase their ability to detect photons, while the cone cells, which function best in bright light, reduce their role. If you have ever stepped out of a bright room into complete darkness, you realize that initially you see almost nothing. Everything is swallowed in blackness. But after just a few minutes, shapes begin to emerge, and after about half an hour, you can see many details that were previously invisible, including the stars in the sky. The key here is that those stars did not change their brightness. Rather, it was your visual system that changed how it processes light signals. This is an extremely important point because it shows that the ability to see stars depends not only on the amount of light, but also on the adaptive state of the eye. In space, astronauts almost never have the chance to achieve this state of full dark adaptation when observing outside the ship, because their working environment is constantly dominated by intense light from the sun, light reflected from the Earth, and light from the spacecraft's own surfaces. Even when they enter a shadow zone, they are still surrounded by artificial light sources like screens, control panels, lighting, and other electronic devices. These light sources constantly stimulate the eyes and interrupt the dark adaptation process, preventing the eyes from ever reaching the sensitivity level required to detect the extremely faint light from the stars. This is not speculation, but a fact confirmed in physiological studies, where it has been measured that the eye's light sensitivity can increase up to tens of thousands of times after fully adapting to the dark. However, the condition to achieve that level is to remain in an environment with almost no light for a long enough period, a condition that rarely occurs in a practical working environment in space. When you combine this with what we've discussed regarding light intensity and distance, you start to see a more complete picture. Not only is the light from the stars extremely weak by the time it reaches your eyes, but your visual system in that specific condition is also not in a suitable state to detect them. As a result, the stars seem to disappear, but in reality they never did. They are still there emitting light continuously for millions or even billions of years. It's just the light is not strong enough to cross your eye's detection threshold while in a light-adapted state. This also explains why, in certain special cases, when astronauts can observe from deep shadow and allow their eyes time to adapt, they can see the stars very clearly, much like you see on Earth on a moonless night in a place without light pollution. This is not just an interesting detail, but direct evidence that the issue lies not in the existence of the stars, but in the observation conditions and the state of the visual system. When you understand this, you begin to realize that what you see is not the entirety of reality, but only the part of reality that your observation system allows you to see under a specific condition. This also opens up a deeper idea that human perception is not a perfect window looking out at the world, but a filter optimized for survival, meaning it prioritizes what is important for existence over what is physically precise. In this case, seeing a bright surface clearly is far more important than detecting faint, distant points of light. That is why your system ignores the stars in bright light conditions. Once you understand this, you no longer view the absence of stars in space as a mystery, but as an inevitable consequence of how biology and physics combine to create the experience you call seeing. What you call light is actually not a continuous thing, but a stream of individual particles called photons. Each photon carries a very small amount of energy and travels through space at a speed of about 300,000 kilometers per second. A number you may have heard many times, but rarely stop to think about what it truly means. Even at that speed, light from the stars still takes a massive amount of time to reach you. Light from Sirius takes over 8 years to reach Earth. Light from the center of the Milky Way takes about 26,000 years. And light from distant galaxies observed by modern telescopes may have traveled for millions or even billions of years before reaching our sensors. Throughout that journey, photons do not cluster into a dense beam, but spread out in every direction in space, like water droplets falling onto a vast lake. The further they go, the lower their density becomes. This is how the inverse square law of distance we mentioned earlier actually manifests at the microscopic level. What you call dim light is essentially just a very small number of photons, reaching your eye or sensor in a unit of time. This is where things become very intuitive if you think about it this way. To see an object, you need a large enough number of photons to hit your retina or camera sensor to form a meaningful signal. When you look at an object directly illuminated by the sun, the number of photons arriving per second is extremely high, enough to create a clear image even with a very short exposure time. But when you look at a star light years away, the number of photons arriving per second is incredibly small, sometimes just a few photons or fewer per photoreceptor cell. In such conditions, the signal becomes very weak, easily drowned in noise, and almost impossible to distinguish if there is another strong light source in the same field of view. This is precisely why stars seem to disappear in bright light conditions, not because they aren't emitting light, but because the number of photons from them is too few compared to the amount of photons from closer sources. This also explains why telescopes must use very long exposure times, sometimes hours or even days, to accumulate enough photons from dim light sources. They cannot brighten the stars. They can only wait long enough to collect enough signal. When you think about this in the context of a space photo taken in a fraction of a second, it becomes clear that there is no way for the faint photons from the stars to compete with the massive amount of photons coming from the sun and nearby objects. This is not a limitation of technology, but a limitation of physical reality itself, because you cannot create more photons from a distant source. You can only receive what actually reaches you. When you put all this together, from the speed of light, cosmic distances, the spread of photons and signal density, you begin to see that the entire phenomenon of not seeing stars in space is not an open question, but an inevitable consequence of how light exists and moves in the universe. A consequence that any observation system, whether the human eye or a camera, must obey. Most of your intuition about the sky was formed while standing under the tens of kilometers of thick air surrounding this planet, and it is that atmosphere that completely changes how light behaves before it reaches your eyes. More specifically, through a phenomenon called Rayleigh scattering. Small molecules in the air like nitrogen and oxygen scatter sunlight in every direction. Importantly, this process does not happen equally for all wavelengths. Blue light with its shorter wavelength is scattered much more strongly than red light. That is why, when you look up at the sky during the day, you don't see a black background with stars behind it, but a bright blue sky that seems to glow from every direction. Sunlight has been mixed into the air and spread throughout the space around you, creating a continuous bright background that completely masks weaker light sources like the stars. If you think about this carefully, you will realize that even during the day on Earth, the stars are still there. They don't disappear, but you cannot see them because the scattered light from the atmosphere is much stronger than the direct light from the stars. This is a perfect example of how the observation environment dictates what you can see. Now remove that atmosphere entirely, as in the environment of space, where there is no air, no molecules to scatter light, and no middle layer to brighten the sky. What you get is not a brilliant blue sky, but an absolute black background, because light is no longer dispersed, but travels directly from the source to your eye or sensor. If there are no strong light sources in view, you will see the stars very clearly. But as soon as a strong light source appears, such as the sun or light reflected from a planet, with no atmosphere to disperse that light into the surroundings, the light becomes extremely concentrated and creates a massive contrast between light and dark areas. In such conditions, faint light sources like the stars are once again completely overwhelmed, not because they vanished, but because they cannot compete with the brightness of the surrounding environment. This is the crucial difference between the experience on Earth and in space. On Earth, the atmosphere blurs the world, reducing the extremes of light and creating an environment that your eye can process more easily. Whereas in space, everything becomes sharp, extreme, and lacks any buffer between you and the light source. This makes sky brighter, not because of a lack of light, but because of a lack of scattering, a lack of light distribution. When you understand this, you begin to see that the black sky in space is not an anomaly, but is actually the natural state of the universe when there is no interfering atmosphere. Everything you see on Earth, from the blue sky to the light of sunset, are just side effects of the atmosphere you are so used to that you consider it normal, while in reality, the universe does not work that way. It is dark, extremely dark, and only light sources that are strong enough or observed under the right conditions appear before your eyes. When you pair this with everything we've said about photons, distance, exposure, and eye adaptation, you will see that the entire phenomenon of not seeing stars in space is not a paradox, but the natural result of how light interacts with the environment and your observation system. There is an interesting detail that, if you don't pay attention, might make you think the whole story ends here, but it actually opens up a more important perspective. What happens if you remove the strong light entirely and place yourself in true darkness? Because when you do that, the stars not only appear, but become astonishingly clear. This is not a hypothesis, but something directly observed in the Apollo missions, particularly Apollo 15 in 1971, when the astronauts had the opportunity to stand in the shadow of the lunar module, an area where sunlight was completely blocked. In that condition, they reported that the sky was no longer an empty black background, but that stars began to appear. Not instantly, not like a flip of a switch, but gradually over time as their eyes adapted to the darkness. This fits perfectly with what we discussed about visual physiology, because when you step into the dark, your eyes do not immediately reach maximum sensitivity, but need time to switch from light mode to dark mode, a process that can take 20 to 30 minutes to complete. During that time, the rod cells in the retina increase sensitivity thousands of times, allowing you to detect extremely faint photon signals that were previously completely invisible. This is why in the same space environment, in the same physical location, you can have two completely different experiences. One where you stand in direct light and see no stars at all, and another where you stand in the shadow and they begin to appear. This has nothing to do with the stars turning on or off, but depends entirely on the surrounding light conditions and the state of your visual system. If you think about this more deeply, you will realize that what we are observing is not a change in the universe, but a change in the ability to observe. The universe does not change when you step into the shadow. Only you change. Your system changes. Your sensitivity changes. And as a result, things that were always there suddenly become visible. This also explains why on Earth you can see a star-filled sky at night, but not during the day, even though the stars never disappeared during that time. When you bring this look into space, where the contrast between light and dark is even more extreme, you begin to see that not seeing stars in photos or when observing under bright light is not a mysterious phenomenon, but just a specific case of a more general law, that the ability to see any light source always depends on the relationship between its signal and the surrounding background light. When that background is too bright, everything weaker vanishes from your perception, but when you remove that background light, even very weak signals can stand out. This is why astronauts, in those rare conditions when they can observe from deep shadow, unaffected by direct or reflected light, can see the stars very clearly, just as you see them from a dark place on Earth. This leads us to a very simple, yet powerful conclusion. Lighting conditions do not just affect how you take a photo or how you look, but actually decide what you can see and what you cannot see. When you understand that, you begin to see that this whole story is not about whether the stars are there or not, but about what conditions you are in when you try to see them. Looking back at the entire picture we have built from the beginning until now, when you put these puzzle pieces together, you begin to see something very clearly that might have been obscured by your initial intuition. We have talked about how camera works, how the human eye adapts, and how light actually exists in the universe. These three seemingly different systems converge on the same result. In bright light conditions, stars do not appear in our perception, not in photos, and not to the naked eye. This is where science becomes very powerful, because when multiple independent paths lead to the same conclusion, you begin to have reason to believe that you are touching upon a true law of nature, rather than a coincidence or a random error. If you look at the camera, you see a system limited by dynamic range, usually only about 1004 to 1005, meaning it can distinguish brightness levels within that range. But in space, the difference between seeing direct light from the sun and light from a distant star can exceed 1,000, a gap so large that the camera simply has no way to record both in the same frame. You might think the human eye would do better, and to some extent it does, because the eye has the ability to adapt and adjust to the environment. But even when you account for the entire adaptation range, the human eye still cannot overcome the fundamental physical limit when there is a strong light source, like the sun shining directly into the observation environment. In a light-adapted state, your eye sacrifices sensitivity to weak signals to protect and maintain the ability to see bright objects clearly. This means that the faint photons from stars, which are already very rare to reach you, become even harder to detect. When you add the physical factor of light, where photons spread out in all directions and their density decreases with distance, you begin to see that the stars do not disappear in a physical sense, but only become too weak compared to the bright background for any observation system to record. This is the most important point, because you are no longer seeing three separate explanations. You are seeing a unified system where each part reinforces the others. The camera gives you a technical limit, the human eye gives you a biological limit, and the physics of light gives you a foundational limit. All of them point to the same thing. In an environment with strong light, especially direct sunlight, faint light sources like the stars will be completely overwhelmed. When you look at this from a scientific perspective, you begin to realize that the surprising thing is not that we don't see the stars in space. It is that if we did see them in those conditions, it would truly be a problem, because it would violate everything we know about light, sensors, and visual physiology. This is why scientists do not consider this phenomenon a mystery needing explanation, but an inevitable consequence of proven laws. When you accept that, you don't just solve a specific question. You learn a broader way of thinking, that when multiple independent systems, from technology to biology to fundamental physics, all converge on the same result, you are no longer facing an open question, but are looking at a law, a part of the deeper structure of reality that you are trying to understand. The most important thing you need to accept is that you never truly see the world as it is. You only see a version of the world that has been processed, filtered, and reconstructed by your nervous system before it becomes the experience you call vision. This is not a vague philosophical idea, but a specific conclusion from cognitive science. Since the 1960s, vision researchers have demonstrated that the brain does not simply record light information faithfully. It actively selects, enhances, and discards signals based on certain criteria. One of the most important criteria is contrast, meaning your brain prioritizes what stands out against the background over what exists but is too weak to make a significant difference. When you place this in the context we are discussing, where light from the sun or nearby objects is extremely intense, while light from the stars is extremely faint, you begin to see that your system does not miss the stars randomly. It actively removes them from your perception because they're not prominent enough relative to the surrounding environment. This is not a bug, it is a feature. If your brain tried to process every light signal with the same level of priority, you would be immediately overwhelmed with information, and the system would be unable to function effectively in helping you navigate and interact with the world. Therefore, through millions of years of evolution, your nervous system has been optimized to do something very specific: focus on what is important for survival in a typical environment. In that environment, perceiving bright, near, and high contrast objects is much more important than detecting faint, distant points of light. This is why, in bright light conditions, your brain essentially shuts off the ability to process weak signals like starlight, because it doesn't receive them, but because it doesn't consider them valuable information in the current context. Vision experiments since the mid-20th century have shown this clearly, such as studies on inattentional blindness, where participants fail to notice obvious objects simply because they do not fit the focus of their attention. Although those experiments are often presented in simple contexts, their fundamental principle applies directly to how you see the sky. When the environment is dominated by strong light, your entire system is tuned to process those signals, and everything weaker is pushed below the threshold of awareness. This is also related to how the retina and brain process signals, where neurons do not just transmit information, but perform calculations like edge enhancement, noise reduction, and brightness normalization, all aimed at creating a stable and useful image, rather than an exact copy of reality. When you understand this, you begin to see that not seeing stars in space is not an isolated phenomenon needing explanation, but a specific example of a broader principle, that human perception is selective, conditional, and limited. This means that what you do not see does not necessarily not exist. It is simply not prioritized for display by our shelf system under those conditions. This is where the whole story returns to a very clear conclusion. The stars have never disappeared from the universe, and their light still reaches your eyes every second. But in the context of intense light and the current processing state of the nervous system, they are not important enough to be displayed in your experience. By accepting this, you not only understand why the sky in space looks black, but you also understand something much deeper, that what you call reality is always a filtered version. And science not only helps you see more, but also helps you realize that you always see less than what actually exists. Another limit you need to recognize, and it is even more fundamental than the issue of bright light or eye adaptation, is that the human eye itself can only receive a very small portion of the electromagnetic spectrum, specifically the visible light range between 400 and 700 nanometers. Everything outside this range, though it exists and carries real energy, is completely invisible to you because the photoreceptor cells in your retina are simply not designed to respond to those wavelengths. This means that when you look at the universe, you never see all the light. You only see a very narrow slice of it, a slice that evolution chose because it was useful for survival on Earth, not because it represents the entirety of physical reality. Beyond that range lie countless other forms of radiation, such as infrared with longer wavelengths and ultraviolet with shorter wavelengths, along with radio waves, X-rays, and gamma rays, all of which carry information about the universe, but fall entirely outside your capacity for direct perception. This becomes particularly important when talking about stars, because not every star emits the majority of its energy in the visible range. Many stars, especially those that are cooler or obscured by cosmic dust, emit most of their energy in the infrared range, meaning that even if their light reaches you, most of that energy cannot be recorded by your eyes. This makes them even more invisible under normal observing conditions. This is why astronomers do not rely on the naked eye to explore the universe, but use instruments designed to observe in other wavelength ranges, such as the James Webb Space Telescope, a telescope launched to operate primarily in the infrared range, allowing it to look through dust clouds and detect galaxies and stars that the human eye absolutely cannot see. When you look at the images sent back by this telescope, you see a universe far richer than what you can observe directly, with structures and light sources that were previously completely hidden. This is not because they just appeared, but because they were always there. You just never had the ability to see them. When you combine this with what we've said about faint light, eye adaptation, and how the brain processes information, you begin to see that not seeing stars in space is not a single issue, but the result of many overlapping layers of limitations. From the physical limits of light, to the technical limits of cameras, to the biological limits of the eye, and finally to the cognitive limits of the brain. Each of these layers contributes to hiding a part of reality from your direct experience. When you understand that, you begin to realize that the universe is not dark in the sense of lacking light, but only dark to you, because your sensory system is not designed to see everything that exists. This is an important conclusion because it shifts the question from why are there no stars in space to why does our system not allow us to see them? And the answer to that question lies not in the stars, but in your own biological limits. Limits that existed long before you began asking this question. The real difference emerges when you no longer rely entirely on your senses, but begin to use science as a tool to expand what you can observe. Science is not just theory. It is a set of methods and instruments precisely designed to overcome the biological limits we just discussed. When you bring these tools into play, the picture of the universe changes completely. A prime example is the Hubble Space Telescope, launched in 1990, a device that doesn't just see better, but sees in a completely different way. It is not limited by Earth's atmosphere, light scattering, or background brightness, as when observing from the ground. Most importantly, it can accumulate photons over a long period, something the human eye and standard cameras can almost never do in direct observation conditions. When scientists pointed Hubble at a seemingly empty patch of sky, as in the famous Hubble Deep Field experiment in 1995, they didn't take a snapshot as you usually do. They let the telescope collect light continuously for several days, specifically about 10 days of accumulated data from hundreds of different exposures. The result was an image containing thousands of galaxies, each containing billions of stars, a staggering number of light sources that were previously completely invisible to the naked eye. This wasn't because those galaxies appeared during the observation, but because they were always there. Their light was just too weak to be detected in a short observation time. By extending the exposure time, scientists allowed the rare photons from these distant sources to accumulate gradually on the sensor, photon by photon, until the signal became strong enough to distinguish from background noise. This is a crucial concept to grasp because it shows that the ability to see depends not just on instantaneous brightness, but on the total amount of photons accumulated over time. While the human eye can only accumulate light for a very short period, usually just a fraction of a second before the signal is reset, scientific instruments can extend that process to hours, days, or even weeks. This turns what is nearly invisible into clear, analyzable structures. If you look at deeper versions like the Hubble Ultra Deep Field in 2004, where the accumulation time reached about 11 days of continuous exposure, you see tens of thousands of galaxies in a patch of sky, the size of a grain of sand viewed from a few meters away. This gives you a powerful, of how much light actually exists in the universe that you never see with the naked eye. Expanding this idea to more modern tools like the James Webb Space Telescope, launched in 2021, you see that we are not only collecting photons longer, but also collecting them in other wavelength ranges that the human eye cannot perceive, especially the infrared range, where many distant galaxies and star-forming regions emit most of their energy. This allows us to look through cosmic dust clouds and detect structures that were previously entirely hidden. The important thing here is that all that light has always existed. It didn't appear because we built telescopes, but only became visible when we had instruments sensitive enough to capture it. When you place this alongside what we've said about the human eye and cameras, you begin to see a clear distinction between natural observation and scientific observation. In natural observation, you are bound by short time frames, limited wavelength ranges, and the adaptive state of your biological system. Whereas in scientific observation, you can overcome all those limits by changing the time, changing the wavelength range, and optimizing signal capture. This leads us to a very important conclusion. The problem is not that the universe lacks light or that stars disappear, but that you are trying to observe an incredibly vast and complex reality with a sensory system designed for a completely different environment. When you replace that system with scientific tools, you don't make the universe brighter. You simply begin to see what has always been there. This is where the whole story becomes. The black sky you see is not a sign of emptiness, but a sign of a limit that science has been and is step by step overcoming by expanding human observation far beyond what natural eyes can do. Now back to the very first question you carried from the opening seconds: why can't we see stars in space? After everything we have gone through, you can realize there is no simple answer like because of X, you don't see them. The reality is that this result arises from a combination of multiple overlapping layers of limitations. When they work together, they create an effect that initially looks like a mystery, but as you peel back each layer, it becomes perfectly clear. First is the technical layer, where the cameras we use to record images are limited by exposure time and dynamic range, meaning they can only record a certain range of brightness differences in a single shot. When placed in an environment where sunlight reflected off astronauts or the Earth is millions of times stronger than starlight, the camera is forced to choose to display the bright parts and ignore the dark ones. Not because the darkness is empty, but because its signal isn't strong enough to be recorded under those conditions. Next is the biological layer, where the human eye, though more flexible than a camera, is still bound by the mechanism of light adaptation. In a bright environment, pupils constrict, cone cells dominate, and the visual system reduces its sensitivity to weak light. This means that even if you look directly into space, you still cannot see the stars if your eyes are adapted to bright light. To see them, you need time to adapt to the dark, a condition that rarely occurs in practical working environments in space. Then there is the most fundamental physical layer, where light from the stars, though powerful at the source, is diminished by distance to the point that when it reaches you, it is only an extremely sparse stream of photons, a signal so weak it is easily overwhelmed by any closer light source. When you piece these three layers together, limited camera, limited eye, and weak light, you begin to see a complete system where every component contributes to the same result. The important thing here is that none of these components are working wrong. The camera is not malfunctioning, the human eye is not broken, and the light does not disappear. All of them are working exactly as they were designed or following the laws of physics. It is that very combination that creates the experience you observe. This is the point where the story shifts from a question about a phenomenon to a lesson in how we understand the world. Initially, you might have thought something was wrong with space photos, but after going through this entire analysis, you begin to realize that the only thing wrong was your initial intuition. That intuition was built from experiences on Earth, where light is scattered by the atmosphere, and the contrast between light and dark is softened. When you take that intuition into the environment of space, where everything is much more extreme, it no longer applies. Science here is not just a collection of answers given to explain a mystery, but a process that helps you recalibrate how you ask the question, so that the question fits reality more closely. When you do that, you see that what seemed confusing at first is actually the inevitable result of very basic laws we have understood for a long time. The most interesting part is not that we found the answer, but that the answer was always there, waiting for you to look at it the right way to see it. There is a very direct way to test everything we have just built, and it involves neither changing the camera nor improving the human eye, but completely changing your position in the universe. When you move away from intense light sources like the sun and venture deeper into space, your surrounding light conditions change significantly. When that happens, the entire way you observe the universe changes as well. The issue all along has not been whether the stars exist, but the competition between light sources within the same observation environment. When you remove the dominant light source in the solar system, you completely alter that balance. In deep space, where sunlight no longer hits directly with the same intensity as it does near Earth, the background light becomes darker and less saturated. In such conditions, faint sources like stars are no longer completely overwhelmed, but begin to stand out, becoming easier to detect for any observation system, whether a camera or the human eye. This is not an abstract assumption, but has been confirmed through deep space exploration missions, such as Voyager 1. Launched in 1977, and now more than 24 billion kilometers away from Earth, it has crossed the heliosphere into interstellar space, where sunlight is a very weak source compared to when you are near Earth's orbit. Although Voyager 1 was not primarily designed to photograph the starry sky, the data it collects clearly shows that when you reduce strong background light, signals from distant sources become easier to distinguish because the signal-to-noise ratio improves. This is the fundamental principle scientists use when designing modern space telescopes. They don't just set sensors more sensitive, they place them in darker, farther, and more stable locations, where light from nearby sources does not pollute the observation environment. A prime example is the James Webb Space Telescope, located at the L2 Lagrange point, about 1.5 million kilometers from Earth. There it can avoid direct light from the sun, Earth, and moon, maintaining an extremely dark and stable observation environment that allows it to detect incredibly faint light from distant galaxies. The important thing here is that those light sources did not newly appear when we moved the telescope away. They were always there. It's just that when you are near strong light sources, you cannot see them. By moving away, you don't change the universe. You only change your observation conditions. This leads to a profound conclusion. There is no single image of the universe that everyone sees the same way. What you see always depends on your position and the surrounding light environment at the moment of observation. If you stand near Earth under the intense light of the sun, you will see an almost empty black sky. But if you move into darker regions of space, that same sky can become filled with stars and far richer in detail. This is not just an interesting detail, but a vital principle, showing that space is not uniform in visual experience. It has no standard state, but changes continuously according to conditions. When you understand this, you realize the original question, why don't we see stars in space, lacks a key element. Where in space? The answer depends entirely on the location and lighting conditions of your observation. When you add that factor, the whole issue becomes clear. The stars did not disappear or hide. They were simply outside your ability to observe in a specific context. When that context changes, what you can see changes with it. And that is how the universe has always worked. In the near future, humans will return to the moon, and this time with much clearer scientific goals through NASA's Artemis program. This series of missions is designed to return astronauts to the lunar surface more than half a century after Apollo. Interestingly, these missions do not just repeat what was done before, but have chosen a completely different location, the lunar South Pole. This area contains deep craters where sunlight almost never reaches, regions known as permanently shadowed regions. This is exactly where everything we have discussed about light, adaptation, and observation will be tested under much more extreme conditions than before. When you place a human in an environment where light is nearly non-existent, you create the ideal conditions for the human eye to reach its maximum state of dark adaptation, something Apollo astronauts rarely had the chance to experience for long periods. In those deep shadows, where there is no direct sunlight and very little reflected light from the surrounding surface, the background light will drop to extremely low levels. When that happens, the stars, which were always there, but hidden by strong light in other conditions, will become much clearer, not because they are brighter, but because their surroundings are darker. This is a crucial point because it shows that visibility depends not only on the light source itself, but also on the entire lighting context you are in. If astronauts in the Artemis program can spend enough time in these dark regions to allow their eyes to fully adapt, we have very good reason to predict they will see star-filled sky, perhaps even clearer than what we see from Earth on a perfectly dark night, as there is no atmosphere to blur the light and no human light pollution. This is significant, not just for observation, but for validation, as it will provide direct evidence in a real-world setting that everything we have said about light, the human eye, and the observation environment is accurate. Stars do not disappear when you leave Earth. They only become difficult to see under specific conditions. When those conditions change, your experience changes as well. Future missions like Artemis will not only help us explore the moon, but also help us test and confirm the fundamental principles of how we see the universe, not through theory or simulation, but through direct human experience in different environments. This is what makes science powerful. It doesn't just offer explanations, but provides ways to test them. In this case, the future of space exploration will act as a giant laboratory where we can literally see how light, environment, and perception combine to create what we call the sky. The most interesting part of this whole story is not that we found a clear answer, but how the original question forced us to rethink what we thought was obvious. If you look at it through the lens of science, everything truly begins not from knowing, but from accepting that we do not know. That sounds simple, but it is foundation of the entire scientific method. The moment you believe you already know the answer, you stop asking questions. And the moment you stop asking questions, you stop learning. In this case, the question, why don't we see stars in space, could have been easily dismissed or replaced with a false explanation if you hadn't maintained that initial doubt. Doubt is not an obstacle, but the most powerful tool you have, because it forces you to re-examine everything, from intuition to data, from how you look to how you measure. When you do that honestly, you begin to see that the world is much more complex than you initially perceived. It is in that complexity that true understanding is formed. Every time you discover one of your assumptions is wrong, you haven't lost knowledge. You are moving closer to a more accurate model of reality. This is vital because in science, realizing you don't know is not a failure, but the first step of progress. Questions like the one we are pursuing are not small questions. They are starting points where you can move from a simple observation to a chain of deeper concepts about light, biology, and perception. This also explains why science never truly ends. Every answer opens new questions, and every new question expands the scope of what you can understand. In that context, not seeing stars in space is not a bug to be fixed, but an opportunity to learn, a chance to explore how different systems, from physics to biology, interact to create the experience you have. When you approach it this way, you start to see that every phenomenon, no matter how simple, can become a gateway to deeper understanding if you stay curious long enough. This is also directly related to how your brain processes information. Humans tend to seek quick, clear, and definitive answers, But science works the opposite way. It accepts uncertainty, works with hypotheses that might be wrong, and constantly checks itself. That is why it is strong. It relies not on faith, but on the ability to self-correct. In this story, you can see that very clearly. Your intuition initially said the sky should be full of stars. And when you saw it wasn't, you had two choices. Either ignore the contradiction or go deeper to understand why. When you choose the second path, you don't just solve a specific question. You learn how to ask better questions. This is the most important takeaway. Science is not about accumulating answers, but about improving how you ask questions. When you do that, the world doesn't become less mysterious. It becomes more interesting. Every time you understand something, you realize there are many more things you don't yet understand. That doesn't diminish the value of knowledge. It increases it by keeping the process of discovery alive. Curiosity plays a central role here, not as a fleeting emotion, but as a long-term driver, a push that keeps you looking, asking, and checking, even when the answer isn't immediately obvious. When you look back at this whole story from that perspective, you see that the important thing wasn't whether you saw the stars or not, but that you went through a process of understanding, a process that began with not knowing, moved through doubt, and ended with a consistent explanatory model. Even that model is not the end point, as it can always be improved with new data or new perspectives. That is the spirit that science, in the way of Feynman, always aims for. Not absolute certainty, but an intellectual honesty, where you are willing to say, I don't know, and use that as the starting point to learn more. When you do that, you don't just understand the universe better. You understand the very way you are trying to understand it. What you have just gone through is not just a solution to a specific question about stars, but a very clear example of how we approach the entire universe. This issue doesn't stop at whether there are stars in space, but expands to a much larger question. How do we understand reality? Looking back at the whole process, you will see a very important thing. Human intuition, though extremely useful in daily life, frequently fails when facing complex physical phenomena. This isn't because it's bad, but because it was built in a very specific environment. Earth's environment with an atmosphere, scattered light, and conditions you've been used to since birth. In that environment, simple rules are enough for survival. But when you leave that environment and step into space where light isn't scattered, where distances reach a cosmic scale, and where the contrast between light and dark becomes extreme, intuition starts giving skewed predictions. This is not an exception. It is a general rule in science. Many great theories, from quantum mechanics to relativity, go against initial human intuition. This leads to a critical point. If you rely only on what seems right, you are almost certain to be wrong when talking about the universe. That is why science does not rely on intuition, but on verification, measurement, and building models that can make predictions, then comparing those predictions with real-world data. In this entire story, you have seen that process happen step by step. We started with a seemingly contradictory observation, a black sky in space, and instead of stopping at the surprise, we analyzed every layer, from how cameras work with exposure limits and dynamic range, to how the human eye adapts to bright light and trades off sensitivity, to how photons propagate through cosmic distances and become sparse, to the role of the atmosphere in creating a blue sky and masking stars during the day, and finally to how the brain filters information based on contrast and survival priorities. Each of these layers does not stand alone, but it links together into a complete explanatory system. Importantly, none of those steps rely on faith. All are testable, measurable, and repeatable. When all those factors converge on the same conclusion, you begin to have a consistent picture, not because it sounds logical, but because it fits every piece of evidence you have. This is where true understanding emerges. Not when you find an answer that satisfies you, but when you have a model that can explain many different phenomena without contradicting itself. This also explains why science never stands still. It doesn't seek absolute certainty, but the best fit for available data. When new data arrives, the model is adjusted, not because the old one was completely wrong, but because we found a better way to describe reality. This is what makes science strong. It doesn't try to protect a belief, but is always ready to correct itself. In this case, you can see it very clearly. Your intuition said the sky in space should be full of stars, and when you saw it wasn't, you could have chosen to ignore or doubt the data. But if you followed the scientific path, you asked questions, checked them, and eventually built a more suitable explanation. This doesn't just solve a specific question. It teaches you a way of thinking, an approach to the world where you don't accept something just because it seems right, but demand evidence, demand verification, and are ready to change your view when necessary. This is the core value of science, not a set of fixed answers, but a method that allows you to move closer to reality by gradually eliminating errors. Looking back from that perspective, you see that the original question wasn't a mistake, but a starting point, an opportunity to go deeper into how the universe works. The most interesting thing is that when you understand this, you realize that reality doesn't need to fit the way you perceive it. Your task is not to make reality easier to understand, but to make your way of understanding reality more accurate. When you do that, you don't just understand why you don't see stars in space, you understand something much deeper. That knowledge doesn't come from believing what you see, but from checking what you think you see. That is the transition from observation to understanding, from intuition to science, and from seeing the world as it seems to understanding how it actually functions. The most important point you can take away after this entire journey is that all the pieces we have examined do not stand alone, but fit together with incredible consistency. When you look at the phenomenon of not seeing stars in space from the perspective of a camera, you see a limitation of exposure and dynamic range that prevents the device from simultaneously recording light levels with such vast differences. When you look at it from the perspective of the human eye, you see a biological system that must adapt to bright light, and therefore sacrifices the ability to detect wave signals. And when you look from the perspective of the physics of light, you see the reality that photons from stars reach you with extremely low density after propagating across gargantuan distances. What is remarkable is not that each of these parts is true individually, but that they all lead to the same conclusion without contradicting one another. No part of this chain of reasoning requires you to assume something extraordinary or break a known law. Everything stays within the scope of principles that have been thoroughly verified in science. This is the strongest sign that you have a reliable explanation. In science, the power of a theory lies not in explaining a single phenomenon, but in its ability to explain many different phenomena using the same set of principles without self-contradiction. In this case, you not only explain why stars aren't visible in photos from the International Space Station, but also why astronauts don't see stars with the naked eye in bright light conditions, why the daytime sky on Earth has no stars, why telescopes need long exposures to record faint light sources, and why in deep shadow stars appear clearly. All these phenomena, occurring in different contexts, are explained by the same set of principles regarding light, sensors, and perception. When you achieve this level of consistency, you begin to see the true power of the scientific method, because it doesn't just give you an answer, it gives you the confidence that the answer isn't random or a coincidence, but the result of a structured system of understanding. This also explains why, when many independent theories, from physics and biology to engineering, all agree with each other, we can trust the conclusion with a much higher degree of certainty than with a single explanation. This doesn't mean science is never wrong, but it means that conclusions supported by multiple independent sources of evidence are far more likely to be correct. In this case, you don't need to rely on faith or speculation to accept the explanation, because every part of it can be tested, measured, and repeated. This is where the story ends in a very clear way. Not with an open hypothesis or an unsolved mystery, but with a firm conclusion that the phenomenon of not seeing stars in space is not supernatural, not a sign of something hidden or unexplainable, but simply the direct consequence of very basic physical laws we have understood for a long time. When you look at it this way, the incredible thing is not that the sky looks black, but that those simple laws can accurately and consistently explain what you observe, from outer space photos to direct human experience. That is why science, when applied correctly, not only answers the question, but eliminates the need to seek supernatural explanations for what already has a very clear solution. The original question remains, seemingly simple, yet opening up this entire journey. Where are the stars when you look out into space? After everything we have analyzed, you begin to see that the answer does not lie in searching for them in a specific location, but in understanding why you do not see them under specific conditions. The stars have never disappeared. They are still there, in their exact positions in the universe, emitting light continuously and without pause for millions or even billions of years. That light is still reaching you right now, photon by photon. The problem is not whether the light exists, but whether your system is capable of recording it in a specific circumstance. Looking back at the whole process, you see that the limit does not lie in the universe, but in the tools and senses you use to observe. Cameras are limited by exposure and dynamic range, so they cannot simultaneously record light levels that differ too greatly. The human eye is limited by the mechanism of light adaptation, so in a bright environment, it loses the ability to detect weak signals. The brain is limited by how it filters information, keeping only what has high contrast and is useful for immediate perception. All these limitations combine to create the experience you call the black sky. But the important thing is that none of those limits come from the universe itself. The universe doesn't change to make you see less. It is your observation system that decides how much you see. This is where science becomes extremely important, because science does not accept those limits as final. It seeks to overcome them step by step, by building better tools, by extending observation time, by expanding the range of wavelengths we can receive, and by placing instruments outside the atmosphere far away from bright light sources. Each of these steps does not change the universe, but changes your ability to access information from the universe. When you look at what we have done, from the long exposure photos of telescopes like the Hubble Space Telescope to the infrared observations from the James Webb Space Telescope, you see that what was previously darkness gradually becomes structure, becomes galaxies, becomes the history of the universe recorded in light. This leads to a very important conclusion. The issue is not whether the universe has enough light, but whether you have the right tools to capture that light. When you have the right tools, what was previously invisible becomes clear, not because it newly appeared, but because you finally have the ability to see it. This is where the whole story reaches a deeper meaning, because the amazing thing is not that you don't see in some conditions, but that you can understand why. From an observation that seemingly contradicted intuition, you can move through a chain of reasoning based on physics, biology, and engineering to arrive at a completely consistent conclusion. That says a lot about human capability, not the ability to see, but the ability to understand. Understanding does not require you to directly experience everything. It requires you to build a model good enough to explain what you see and what you don't see. When you do that, you begin to see that the world doesn't become less mysterious, but clearer in a deeper way. A way based not on feeling, but on the consistency of laws. The greatest joy is not having the answer, but the process of finding it. The process of questioning, doubting, testing, and finally understanding a small part of reality. When you look back at the original question once more, you no longer ask, where are the stars in a physical sense? You understand that they are always there. It's just that you were looking at them with a system that wasn't enough to see them. Recognizing that, accepting your limits, and seeking to overcome them is the most incredible thing in this entire story. Don't forget to hit subscribe so you don't miss the next interesting science stories. See you in the next video, where we will continue to explore the greatest mysteries of the universe.